Uh-huh. Okay, let's continue to talk about transformations for all kinds of things. Mainly is camera animations in this lecture, but you can animate basically anything with what you learn now. So just as a reminder how our transformation matrices look like, we can have a translation component, which you can always find in the last column. You can have scaling components, or in the diagonal elements of affine transformation matrices. And our rotation matrices, as always, look scary, but really you only need these as tools and then plug in whatever you like when you know the axis around which you want to rotate and the individual angles here. So you always assemble the rotation matrix based on two individual components: rotation around X, rotation around Y, and rotation around Z. So let's consider a few more complex transformations. So something we want probably to do in, say, flying scenes, in where my camera moves around and looks at the scene from different angles. So we basically need to move in every frame in such scenes the viewpoint, our origin, to a specific viewpoint C, and we want to orient our viewing direction, our set here, along a given direction, starting at that viewpoint, so that we can fly around through a scene and look anywhere along a given direction. That allows us, as mentioned in the previous lecture, that always allows us to use the same simplistic or simple projective math. Right? We always project on one plane that lives in a zero coordinate, so in the xy plane of our coordinate system. Makes things very, very easy. But we can still move around and look at things. So what we want to do is we want to work out these sort of translations relative to a 3D scene. Now, again, we want to do this probably for perspective transformations. So the canonical form of this is really just that we need this parameter f, and we look along the z-axis into the negative z-axis into our scene. So in this lecture, we will mainly talk about the step we mentioned briefly last time to transform that viewing orientation to viewing vector d, starting in a coordinate C. So that entire viewing coordinate system, projective coordinate system, moves to our new viewing coordinate system here, positioned in the viewpoint, a new viewpoint parallel to this new direction D. So the required steps for animations are always pretty similar. We want to translate the origin to our new point. We need to work out a translation, a transformation, a rotation around the y-axis, and we want to work out a rotation around the x-axis. So we want to align the z-axis, so we need rotations around the x-axis and around the y-axis to make this happen. We don't need all three of them because, of course, this is ill-defined, so this can end up anywhere. We just want that parallel. Parallel vectors does not have no notion about intrinsic rotation of a vector. So the two rotations are lining up the z-axis with that view direction. That's what we want to achieve. So we want to translate the origin, and then find a rotation matrix that consists of two individual rotation matrices. So the rotation component, the translation component of our transformation matrix, is relatively straightforward. Of course, we want to bring that new point down into our new origin. So all we need to do is to take the coordinates of this point C and negate them to move that point to that origin back down. So then we end up with the origin C at the same point. So our transformation, our translation matrix looks simply like this: minus Cx, minus Cy, and minus Cz. Now the rotation matrix is not as scary as it looks. We really just want to use the trigonometric form of what an angle actually means, right? What an angle translation actually means. So if you look at that plane, we want to first figure out a translation, a rotation in a specific plane. When we want to rotate around a specific axis. So in this case here, I have Z and X on the plane here, so inside here, and I want to rotate around Y. Okay, Y is coming out of the screen here. All right, so I want to work out what that V component needs to become to align with one of my axes and one particular one, my Z axis, right? I want to align D with my Z axis. So I want to first figure out what a random vector in our plane. So that plane is somewhere here. This vector is somewhere here. How do I need to rotate this so that these two co-align? So this is what I want to work out here. So all I need to do is to plug in into my rotation matrix, and then basically just work out the difference between our vector D and the angle here to this plane. So I just really need to work out that angle and just calculate it based on this. So this is just how cosines and sines are defined originally, right? The fractions of these two vectors give you the angle. Okay, we do the same for the YZ plane. So the YZ plane is now here. The x-axis is now what I want to rotate around, but we are already in this plane now. Okay, so we have now worked out how to rotate this vector so that it aligns with the YZ plane. And now all that's left to do is to rotate this vector, or rotate the entire coordinate system so that it co-aligns with D eventually. So first, we have a vector like this, somewhere arbitrary in space. We first work out how to translate this around Y so that it ends up parallel with the Z-axis. So it's still not parallel, it's just in the plane somewhere, right? And now all we have to do is to work out how to co-align this with Z. So in this, affine transformation matrix are always invertible, so I can show it either by moving this or by rotating this. Right, so I show it again by moving the coordinate system. So if I move the coordinate system, I move the coordinate system first so that it aligns with the vector in the plane, and then I move the coordinate system so that it aligns with the direction vector. Okay, and then I can again just work it out through D, and what I get then is three matrices. So first I have my translation matrix, then I have my rotation matrix around one axis, and then rotation matrix around another axis. Sorry, the other way around. This is just confusing with C. So I first my translation matrix. I'll show you again here. So this is A, is my translation matrix. So A is my translation matrix, moving the new viewpoint position down to the origin. Then I have B, my rotation around the x-axis, and then a rotation around the y-axis, I think it was. No, first y-axis, then z-axis. Y-axis, z-axis. Multiplying together gives me a single transformation matrix so that I can transform every single point in my scene and modify every point in my scene so that it now looks like if I would look from an arbitrary position, right? Well, all I do is transforming this so it looks like that. I leave my viewing, my camera and my viewing coordinate system constant. It looks still always like down like this, and all I do is move around my object so that suddenly it looks like as if I would look down that way. But this is the transformation matrix I need. So I can either transform that entire world coordinate system around, or invert the matrix and transform that whole object around, and it will always be the same. It will always look the same. What you don't want is to go away from the notion that the camera lives somewhere here in the origin, for example, your view plane somewhere parallel to a plane in your coordinate system, and that the projection is easy, because you don't want complicated projection calculations here. So we call this also that few coordinate system. We also call that a canonical form. So that's a kind of canonical coordinate system. When I have transformed all of my vertices in my scene, then it's in a canonical form, and I can evaluate my camera matrix. So the one thing in that approach, what we haven't really looked at is the vertical. So if I look down somewhere here and I have now my view plane parallel to something, my view direction parallel to something I want to define, what I don't know is how my vertical actually is aligned relative to it. So I can come out any way mass allows you here. Will be constant, but you have not really control here about these kind of verticals. So usually the y direction is treated as the vertical, and by doing the ry transformation first, things should work out correctly. So it should look up first. If you do the rx translation first, or rotation first, then you might end up with a flipped y coordinate, and that's not great, especially if you probably flip around, then you're going up, down, then you flip your scene all the time. This is not great. So be careful with that. We'll look at an alternative way to work out these kind of transformations just in a few slides. A very popular exam question is something related, which is just the rotation of an object around a given line. So what you get is a point and a direction, which is a line, and it's an arbitrary line in space, and an object. And the question is to work out a transformation matrix that moves that object around a certain angle around this arbitrary direction. Right? This is an x, y, z component direction vector. And again, it's the same principle. It's the same principle. What you want to do is to break up your transformation into Rx, Ry, and Rz components and a translation. So if this lives somewhere in space, the first thing you always want to do is to move this to your origin, and then align this arbitrary angle with one of your axes. You choose any axis, okay? You just need to be aware which one. So you have that now parallel. Then you do your rotation around that axis. Just define on, in this case, your RZ, right? So just define your angle translation now around RZ, and then undo all of this. To go back with the rotations, go back, and then move it back. Move the object back then again to where you got it from. And you get a rotation around an arbitrary line. This is exactly the same principle as I just explained to you here. So again, make the line of rotation one of the Cartesian axes in your coordinate system. Make it the same thing. And doing the rotation then around this axis is much easier than working out a rotation matrix around 3 arbitrary axes. And then restore it back to its origin. So really how this looks like, and this is always how transformations basically look like. It's always you want to work out something that goes back to the origin, so that matrix A. So it moves your object from wherever it is to the origin. Then we rotate everything so that this axis you're interested in aligns with one of the axes. Then we apply our rotation around this axis. Around this axis, here in this case, just by choice, is RZ. I rotate that object here. In the origin, I rotate it around. And then I undo all of that in the opposite order. I rotate back, and then I move to somewhere. Okay? So this is again, this is a popular exam question. So probably have a look at that. Okay, you can. This is the same principle for all sort of object-centric manipulations. So if you want to scale this to whatever that size, then always what you would do is to move it from wherever it is, collect it wherever it is, move it to the origin, then apply the translation, and then move it back to where you got it from. And then you can also scale, of course, just in certain directions and share the object. And well, what you want to do then again is to align with your coordinate system and then do the primitive operations just along the axis you're most familiar with. So usually the projection and drawing of a scene comes always after all the transformations. So we transform, we animate objects, we transform everything, then we transform everything from our world space into our viewing space coordinates, you know, where my viewpoint is always at the center, always at the origin. My viewport is always at the origin. My view plane is always fixed and in a parallel setup to one of the planes. So there is therefore convenient to combine the projection with the other parts of the projection. If I only want to do all of that just once, I just do that multiplication once and then apply this multiplication, this combined matrix to all of my vertices again, just to save space. Okay, let's see how the projection matrices actually look like. And in the last set of slides, we worked out what these actually do. So for the autographic projection matrix, really for the canonical form, the view form, we only need to drop the set coordinates. So all we need to do is to put in a 0 here. And if we multiply this with any vector, that third component becomes 0. And of course, you see this is the orthographically projected point on a plane. Now the perspective projection of homogeneous coordinates can be also done with matrix multiplication, and in this case here we need to work out that scaling factor, right? That scaling factor is now applied on x and y, and every set component of our vectors becomes the f distance of our parallel x or y set plane from the origin. So the way I can do this is I can just plug in here at that fourth component 1 over f. You can plug it in and work it out in homogeneous coordinates just by the matrix multiplication form and then solve that. Then you will see that this is what comes out as 1 over f. So basically what I use is this homogeneous coordinate scaling factor to make that scale happen correctly for x, for y, and for z. So now if I scale this back to Cartesian coordinates, so to the actual coordinates of my projected planes on the 2D plane, then I divide by this last component, right? To scale back from homogeneous coordinates to Cartesian coordinates, I always divide to the last component. So we can normalize this back. If we divide by this, we get x times f over z, y times f over z, and f. So f, we knew is the component. This is the scale factor. So apparently it depends on how far something is away and how far the f plane is away from our origin. This is something we already intuitively worked out in the last set of slides. So projection matrices are most of the time, I would say probably always, singular. The intuitive explanation is, of course, well, if you project something from 3D to 2D, you lose one dimension of information. So you can't simply undo this, except you keep track of what you lost. If you just think about taking a camera taking a picture with your smartphone camera, you simply can't reconstruct a 3D scene from it because of occlusions and because of that lost depth component. If you keep track of the depth component, you can sometimes, most of them invert, but usually you would need to assume that the step after you integrated your projection, your entire matrix becomes non-invertible. You can't undo your transformations in 3D space then simply from that matrix. So that's why most of the time people leave the kind of projection part conceptually separate from the transformation part, but altogether to have it then efficiently processed, what you do is to multiply them all together and then just apply one matrix to every point in your scene. So let's have another quick second look at homogeneous coordinates. There is a small caveat to that scaling formulation, and probably you would have already thought about it or you watched the other videos from the older lectures. What is if this scaling factor here is becoming 0? What if this is 0 very small? Well, you can't divide by 0, so that will all become undefined. We need to treat that special case as what it is, a special case. And really, we have two types of homogeneous coordinates. Again, take out your notepad and make a note. This is very important to remember and to know. There are two types of homogeneous coordinates. Either we have a non-zero element here in this last S, then it's a position vector. It's always a position vector. It's somewhere, it's a point in space, right? It's somewhere in space. If that scaling component is 0, then in the final ordinate, then this is a direction or magnitude. It's a direction. The direction will always point in the same direction. It doesn't matter where that vector starts, right? So your ordinate in this case, the last one is 0. So that's direction. Direction if there is 0, position is if there is not 0. Okay? There's non-zero entries. So this makes intuitively sense. If we add two direction vectors, we obtain a direction vector, right? If we add these two together, this will stay 0, and all of these will be added. So adding a direction vector and a direction vector, you know what happens. You get that thing here. So you get a new vector, and then this is actually a new direction. But it doesn't matter where it is in space, right? If we add a direction vector to a position vector, we obtain again a position vector. Yes, that's true. So we have a position vector. We add that direction vector. So we move that point to here. We get a new position vector. Yes, makes sense intuitively. What doesn't make too much sense intuitively, if we add two position vectors, we obtain their midpoint. Of course, it makes sense if you put everything into perspective with the origin. Yes, then you add together two vectors starting in the origin and you get their midpoint. Yeah, but this is it hasn't really meaning in normal vector geometry. It's a valid operation, but all you would get is the same as you would have just added direction vectors, but only always relative to the origin. Okay, so let's have another more detailed look at transformation matrices. Really, with that knowledge of position vectors and direction vectors, what we see here is that these transformation matrices consist of columns of vectors here. So we have 3 direction vectors in this column, in this column, in this column, Q, R, and S direction vectors, and 1 position vector. So this was our translation. This was our rotation, right? So, and what if you now take a second or so and think what these 3 could be? It's becoming really, really interesting what this transformation matrix actually does. So assuming the bottom row is always 0, 0, 0, 1 here, what we get is that the last ordinate is not affected by any translation. Okay, the position vector here in the last ordinate means that all vectors will have the same displacement here. So this position vector, if I put in a position vector here and multiply a position vector, I will move all of them with my translation and whatever comes in out here with the translation. If I put in a direction vector here and multiply the direction vector with the transformation matrix, this will just ignore that last column here, right? That 0 will 0 that out, so all you do is rotation. So if you do not share the object, these 3 vectors, so if I apply, if I say these 3 vectors Q, R, and S are 3 vectors like this in our coordinate system, which are orthogonal here, by the way, right? So if I do not apply any sharing operations in my transformation matrix and only use what we learned to this point, translation, scaling, and rotation, then after applying this matrix, whatever I do here, after applying this matrix, these axes here, Q, R, and S, will also be orthogonal, right? So, and what it also means is that the effect of these axes here, so these axes here, these columns here, are really the axes after the transformation, and it doesn't. I don't have to keep them orthogonal. If I take any of these and say, okay, no, now my new vector is actually defined like that, what I did is a sharing operation, right? So I have now a vector coordinate system after the transformation that is not orthogonal anymore, but still valid. It's still an affine operation. every parallel line will be parallel after that. It will just be shared. So let's see. Okay, so this is just showing the transformations here. How I can apply this to my coordinate system. Okay, again, if I transform the origin by my transformation matrix, what I get is obviously the translation component of it, because this is what I just saw before, where I moved my new viewpoint, for example, to a new origin. So the columns are the original axis system after transforming. So that's the same as if I would take this coordinate axis and transform it. Then I get a new one. So this is the new coordinate axis after transformation, and this is the new origin. This is all it is. So it's the Q is the transformed x-axis, R is the transformed y-axis, and S is the transformed z-axis, and C is the transformed origin. So this is how you read transformation, affine transformation matrices. Yeah, and getting back is always, you can always invert these matrices, and then it gets you back to the original transformation. It's harder to factorize. So if you have put together many transformations into a single transformation matrix, you can't factorize the individual ones out anymore. You can just undo that entire thing at once. So usually what happens is we are not given the transformation matrix that moves the scene around. So before we had transformation matrix, and we could actually work out if we transform that to parallel to a direction we want to view along, then we just apply, we basically multiply the transformation matrix with our coordinate system. So we don't have that. We only have, like in this case, this probably viewing direction here, or we want at least one of our axes to be parallel with that viewing direction of a new coordinate system like UVW. So there is a way to abuse and use the dot product to work out this, to work out how the transformation matrix, how to transform a coordinate system like this to make it parallel to another vector. And the dot product really, you used it so far to work out angles between vectors, and with probably little intuition of what it actually does. But really what the dot product does, you can sit down and plug in the equation for dot product. What it does is it projects a given vector onto another vector and gives you the ordinate, the kind of projection component along that vector. So it gives you how long do you need to travel, so like this, how long do you need to travel along that vector to get to the point if it's projected onto that vector. So this is the dot product, and this is of course relative to the angle of the two. So this is relative to the angle of the two. That's why you can actually work out the angle from the dot product. And you can work out if two vectors are parallel, and you can work out if two vectors are orthogonal. That's probably you should write down on your cheat sheet what if your dot product is 0, and what does this mean, and these sort of things. But here, what we use is the dot product to establish a projection. And the dot product itself is defined as, well, the magnitude of P and U times cosinus theta. And so if U is a unit vector, then I can leave out this magnitude here, and I can just say that if both of them are unit vectors, so if this is a unit vector, this is a unit vector, then it will be the magnitude of P times cosinus theta. So, and also if U is along a coordinate axis, then P dot U is the ordinate of P in the direction of U. So if I have what I showed you earlier, if I have this projected onto this vector, so say P times U here, U along this vector, then what you get is the projected magnitude on this vector. So if we extend that to 3 dimensions, we can see that a change of axis can be expressed as a projection using dot product. So what I want to have is that, you know, in the last videos, we use this to work out a translation of the coordinate system first into the plane and then along one chosen axis. Now what we can also do is to choose 2 axes and just to project it on it. I'd first project it, for example, onto X and then project it onto Z to make them parallel, to work out the axis I need to establish a new transformation matrix. So I can do this in one stop, also with a transformed origin. So the only thing I need now is a new vector p minus c. So that's the vector from the new origin to a point P. So this is a point P. This is my new origin. What I want is this point P represented in this new coordinate system u, v, and w. Right? And the way I do this is I project this point onto this new coordinate system to work out, actually onto one of the vectors, one of the axes here, to work out, assuming orthogonal other axis, to work out the transformation matrix from that coordinate system to that coordinate system. So the way to do it is simply again by plugging in. So giving a point P in that coordinate system, right, in X, Y, and Z, a world coordinate system, we can basically calculate the corresponding points by just plugging that in, what I just said before, by doing it for each of the components. So if I have Px, that new vector representation of our P in our new coordinate systems, dot U, right, I project it on U, I project that new vector on V, and I project a new vector on W. If you work that into the brackets, so you get the result is basically this P dot U minus C dot U. And that whole thing I can rewrite into matrix notation, and this should already look very familiar. So I have this new coordinate axis with all the X components, or the Y components, or the Z components along this new transformed coordinate system, and a transformed coordinate origin towards the new origin of the of these 3 components. So the scaling needs to be correct here, of course. So and now we are in full control of what the verticals are actually should do, right? I can just say that if we assume that this new V direction here is the vertical, so this here, right? That should be the vertical. We can constrain it to be always upwards. So first I had the problem that if I look down the Z direction here, I had the problem that if I'm not careful and don't do the rotations in the right order, then I might end up with a flipped coordinate system and a flipped projection plane. And I don't want that. So now I can be in control and can say, okay, this always looks up. This is always 0, for example. This always looks along the 0 components, parallel to my original y-axis. Now, if you run this original program, so give them a view point C, right? So here is the C viewpoint, and a view direction D, right? We don't see D here, but let's say it's running along one of these. Then we need to find a transformation matrix that gives the canonical view. If we do this by finding these vectors in the new coordinate system, then we can represent all of these new axes in our new canonical coordinate system by that new direction vector D. So we can rewrite this W. If we say this is our new viewing direction, okay, let's choose this. Then it's just the unit vector of D. It's just the unit direction of D. And so we can write also U in terms of some vector P in the horizontal direction. That doesn't really matter. I can choose, and I can say that P, in this case, is some vector P, has to be, the Y component has to be 0. So I want to make it parallel to my original coordinate system. So this has no vertical component, which is great. I'm in full control of that. So Q, I can say, is some other vector in the vertical direction, and this I can again write as a normalized version of that vector, and say, okay, V is some normalized vector in this vertical, and I can say that this must have, the y component here must have 1. So I have ensured not only that this has no vertical component, but that this is orthogonal to this view and always looks up, always positive up. So I'm now in full control of this, and this moves and always like that. And this can, of course, then rotate like that. I can look everywhere I want, but I know that this will always look up and this will always look left or right in your case now. So we have 4 unknowns. I know that these I have already plugged in. I don't know px, I don't know pz, I don't know qx, and I don't know qz. And to solve this, I know that these two are orthogonal to my new view direction, right? So this has to be orthogonal because I just defined it like this. So this has to be orthogonal, so I can plug it into the cross product. So P and Q cross should result in a vector I know already. And this vector I know already is D, the vector I want to align with. And so we can do this because the magnitude of P and all of these, this is not really set yet. I've just defined it needs to be a unit vector along these directions. So we evaluate this with the cross product. Just plugging in gives us correspondence equations where we say dx equals minus pz, dy is a slightly longer term, and dz equals px. It's just by working it out, by plugging it into the formulation of the dot product. So we can write our vector p completely with components of our desired direction vector d. In this case, it's dz, 0, and minus dx. So this is our new vector p. And the same we can do for q, and then putting these things together. Well, if I do p times q, I know it's orthogonal, so I can also plug it in the definition of the dot product. And having that orthogonal, just plugging that in gives me another equation, which gives me the last unknown, and I can work out with simple linear equations for q and p how they are represented in terms of d. So then I can just go back and plug into this original formulation. So u is the unit vector along direction p, which is a 0 y component. V is the unit vector along direction q with the 1 y component. W is our view direction, so I can plug that back in. We know already c, which is our origin, and I have my transformation matrix defined simply by using the dot product along a few given viewing direction and the transformation of my viewing coordinate system.